Hello, I am Brian Leslie, one of the physics tutors at ClassRx. ClassRx is an online, STEM-focused private tutoring company. My background is I have a PhD in physics, and over the past 10 years, I've been teaching physics and STEM engineering at the high school level, as well as tutoring at high school and college levels. In the next few minutes, I will show how to approach and solve a free response question in the AP Physics 1 exam. This is a free response question from section 2 of AP Physics 1 in 2018. The exam is 90 minutes. There are 5 questions. You need to answer them all. And 3 are short form, typically taking about 30 minutes to complete and are worth 7 points each. And the longer form ones are about twice as long, but 25 minutes and worth 12 points. This is a force problem. It's the situation of motion of a spacecraft in orbit, circular orbit around the Earth with a radius r. It gives the mass of the Earth as m capital E, and the mass of the spacecraft is small m. The first question asks to draw a free body diagram identifying the forces on the spacecraft. And that's a typical introduction to a force problem. It should be fairly easy to answer. This is the geometry of the situation. This is the central body of the Earth, the spacecraft in its orbit around the Earth at a radius r. This is distance r. And there's only one force acting on the spacecraft. It's acting radially inwards, pointing towards the center of the Earth, and it's due to the gravitational interaction between the two bodies. It's usually given as F sub g and equal to g times the mass of the first object, me. Second object is the mass of the spacecraft divided by the square of the distance separating them. So fairly easy problem, but it allows you to proceed to answer the second part of the question. So in the second question, question 1b, they want you to derive an equation for the orbital period t of the spacecraft in terms of the masses and the separation r between them. And a usual warning not to add any additional details to the part 1a. This might be needed to solve the problem. Again, it's a fairly standard approach to a force problem. Forces ultimately come down to identifying the net force on the body of interest. And using Newton's second law of motion, we know that the net force is equal to the mass of the object, which is m in this case. We're interested in what's happening to the spacecraft, times the acceleration of the spacecraft. We know the spacecraft is in a circular motion, and so we know the size of this acceleration. It must be v squared over r, pointing radially in towards the center. It's a centripetal force or acceleration on the spacecraft. We can put these two facts together to get the size of the net force. It must be m v squared over r. But we already know that part 1 that there is only one force Fg acting on the spacecraft. So F net must be equal to the gravitational force G me m over r squared. And so we've got two ways of calculating the net force. One from the inertial properties of the motion of the spacecraft, mv squared over r, and independently the gravitational force on the satellite. These must be equal, the same, and so we can have a equation which relates these two. Mv squared over r must equal g me m over r squared. This can be easily simplified. We notice that m, mass of the spacecraft, appears on both the left and right hand sides of the equation. They can be cancelled. Also, we've got in the denominator an r here, r squared on the right hand side. We can cancel one of those. And so simplifying this expression, we get a simple equation for the square of the velocity is equal to g times the mass of the Earth divided by the radius of the orbit. Doesn't depend on the mass of the spacecraft at all. And so we can take the square root of both sides to get an expression for the velocity, or the size of the velocity, which is the speed of the satellite. To maintain this orbit must be g me over r, all square rooted. But the question is asking what's the period. We now have an expression for the speed, and we're going to use that to calculate the period. The period is just the distance, that is the time it takes for the satellite to make one complete orbit. Because it's going at constant speed, the formula for the period is just the distance traveled divided by the speed of motion. The distance for a circle is just 2 pi times the radius, that's the circumference of the circle. And the speed we've calculated just the size of v, which is square root of g me over r square rooted. We put these two formulas together, we get the equation for the period as 2 pi r over the square root of g me over r. Again, we can simplify the equation a little bit, and we get 2 pi over the square root of g times me, and gather the r terms, we've got r to the power of 1.5. If you square both sides, and that's the answer. If you square both sides of the equation, you get t squared. There's a bunch of constants times r cubed. And this is just Kepler's third law of planetary motion. There are additional parts of the question. I won't go into those in detail just now. Thank you for watching the video. If you want to contact us or have any more questions, please visit www.classrx.com. Or drop us a line at hello@classrx.com, mentioning my name, Brian Leslie, in the subject line. Thank you.